Clarke L. Hull. Hull received his Ph.D. from the University of Wisconsin in 1918, where he also taught from 1916 to 1929. In 1929, he moved to Yale, where he stayed until his death. Hull's career can be divided into three separate parts. The first part was his concern with the testing of aptitudes. In fact, his first book was entitled Aptitude Testing, which was published in 1928. The second part of Hull's career was concerned with hypnosis. After long study of the hypnotic process, he wrote his second major book entitled Hypnosis and Suggestibility, which was published in 1933. The third part of his career had to do with learning theory. His first book on learning theory came out in 1943 and was entitled Principles of Behavior. His final book on learning theory came out in 1952 and was entitled A Behavior System. He intended to write a third book on learning theory, but he never got around to writing it. Hull was a cripple most of his life. He suffered partial paralysis from polio, which he had while he was rather young. In 1948, he suffered a coronary attack, and 4 years later he died. In his book, A Behavior System, the last book he wrote before he died, he expressed regret that the third book that he intended to write on learning theory would never be written. Even though Hull felt his theory was incomplete, it had a profound influence on learning theory throughout the world. Kenneth Spence, one of Hull's many famous students, states that 40% of all experiments in the Journal of Experimental Psychology and in the Journal of Comparative and Physiological Psychology during the period between 1941 and 1950 referred to some aspect of Hull's work. When only the areas of learning and motivation are considered, this figure rises to 70%. In fact, it's still common for the student of learning to come across numerous references to Hull's work while going through the psychological journals. By any measure, Clarke Hull was a major contributor to our knowledge of the learning process. Clarke's approach to theorizing utilizes what has been called a logical deductive or a hypothetical deductive method. His theory was a logical structure of postulates and theorems, which is very much like Euclid's geometry. The postulates are general statements about behavior, which cannot themselves be verified. However, from these postulates, theorems are generated. The theorems follow logically from one or more of the postulates, whereas the postulates themselves are not testable directly. The theorems that they generate can be tested. Experiments are designed to test the theorems, and if the experiment comes out in a predicted direction, the theorem is said to be correct and the postulates upon which it is based are supported. If the experiment does not come out, the theorem is said to be incorrect, and the postulates upon which it is based are thought to be in error, and therefore they must either be revised or abandoned. It can be seen that this type of theory creates a dynamic, continuously changing, open-ended system. Hypotheses are constantly being generated, and some of these are supported by experimental outcomes and others are not. When experiments come out in the predicted direction, the theory, with its postulates and theorems, is strengthened. When the experiments do not come out as predicted, the theory is weakened and must be revised. So this open-ended theory is continuously updated by the outcome of empirical investigation. It should be pointed out that the theory, any scientific theory, is merely a tool that aids the researcher in knowing where to look for new information. It suggests research possibilities. This is the heuristic nature of a theory. Again, the heuristic value of a theory is its ability to generate new research ideas. The ultimate value of a theory is determined by whether or not it agrees with observed facts, or in this case, with the outcome of experiments. So in science, the ultimate authority is the empirical world. Everything else is simply a means to that end. A theory such as Hull's can become very abstract and removed from the empirical world, but still it must ultimately make statements concerning observable events in the empirical world. In other words, no matter how elaborate and abstract the theory becomes, it must ultimately be reduced to thing language. That is, it must make verifiable statements about things in the empirical world, and this is exactly what Hull's theory was attempting to do. There are three major kinds of events in Hull's theory. First, he has a number of independent variables. These are stimulus events systematically manipulated by the experimenter. The second kind of event in Hull's theory is a system of intervening variables. These are events thought to be taking place within the organism but are not directly observable. Third, he has dependent variables. Dependent variables are those aspects of behavior measured by the experimenter in order to determine whether or not the independent variable had any effect. Dependent variables are always some form of behavior. We'll summarize the major aspects of Hull's theory by looking at a few examples of each of these three kinds of variables in a moment. But first we'll turn to a few other important components of his theory. One of the most important characteristics of Hull's theory is that it is a reinforcement theory of learning. More specifically, it is a drive reduction reinforcement theory of learning. A biological deficiency in the organism produces a drive state or a need state. Each need or drive has specific stimuli associated with it, which are called drive stimuli and are symbolized S sub D. An example would be the hunger pangs that are correlated with being hungry. The dry mouth and lips that accompany thirst would be drive stimuli specifically associated with the primary drive of thirst. Only stimuli which can reduce drive stimuli can be reinforcers. The reduction of drive stimuli is what Hull called reinforcement. So we have a biological deficiency of some kind. In other words, the organism is lacking something that it needs, such as air, water, food, or sex. This creates what Hull refers to as a need state or a drive state. But each one of these drive states have stimuli specifically associated with them, which are called drive stimuli. Only those events that are capable of reducing drive stimuli can be reinforcers. With Hull's theory, it is important to differentiate between a reinforcer and reinforcement. A reinforcer is a stimulus which is capable of reducing drive stimuli. Reinforcement is the reduction of drive stimuli. So there is an important difference between the two. Many theorists talk about reinforcers without talking about the underlying process which constitutes reinforcement, but Hull talks about both. Originally, Hull had a drive reduction theory of learning. Later, he revised it to be a drive stimulus reduction theory of learning. The reason he changed was because if a thirsty animal is given water as a reward when he does something you want him to learn, it takes a long time for the actual thirst drive to be satisfied by the water. The water must get into the system, it must get into the blood, and its effects must ultimately reach the brain. Eventually, after giving a thirsty animal water, the thirst drive will be reduced. But this is sometime after the ingestion of the water. So the mechanism of drive reduction itself was too far removed from the presentation of the reinforcer to explain how learning took place. Because of this, Hull revised his theory to say that the drive stimuli reduction is all that is necessary for learning to take place. And as we mentioned a moment ago, this includes such things as the dryness of the mouth, the parched lips, and so forth. These are things that are relieved immediately when the water is presented to the thirsty animal. Thus, in its final form, Hull's theory of learning is a drive stimulus reduction theory of learning, which means all learning depends upon reinforcement, and reinforcement consists of the reduction of drive stimuli. Say we have a stimulating condition, and we have a response on the part of the organism to that stimulating condition. If that response leads to the reduction of drive stimuli, the association between the stimulating condition and the response that led to reinforcement is strengthened. The more often that stimulus leads to that response, which leads to reinforcement, are paired, the stronger the association between the stimulus and the response become. As the association becomes stronger, there is an increased tendency for the organism to make that particular response when he is stimulated in that particular way. That whole thing again is as follows. If a certain situation, a stimulus, is followed by a certain response, and if that response is followed by reinforcement, the association between that stimulus and that response is strengthened. Or it can be said the habit of giving that response to that stimulus gets stronger. Or, according to Hull, the habit strength increases. Habit strength is one of Hull's most important terms, and it refers to the strength of an association between a stimulus and a response. As the number of reinforced pairings between a stimulus and a response go up, the habit strength of the association between the two goes up. However, habit strength goes up in a rather complicated way. Hull had a mathematical formula to describe the nature of that relationship between the number of reinforced trials and habit strength, and it is as follows. Habit strength, was symbolized SHR, is equal to 1 minus 10 raised to the minus 0.0305 n power, where n refers to the number of reinforced pairings between a stimulus and a response. This formula generates a negatively accelerated learning curve, which means that learning takes place as a function of reinforced pairings between S and R with diminishing returns. That is, the early reinforced pairings have more of an effect on the learning process than do later ones. In fact, a point is reached where additional reinforced pairings between the stimulus and the response have no effect at all on habit strength. So early learning is more rapid than later learning, or early reinforced pairings between the stimulus, or capital S, and the response, or capital R, are more influential than later reinforced pairings, and this generates a negatively accelerated learning curve. Learning, according to Hull, is only a function of the number of reinforced pairings between S and R, and no other factors influence it. Habit strength is the only part of his theory that says anything at all about the learning process. All the other variables that we will consider in a moment are performance variables rather than learning variables. So in Hull's theory, it is very important to differentiate between learning and performance. In order for a learned response to occur, habit strength needs to be activated by drive. Drive does not direct behavior, it simply arouses it and intensifies it. Without drive, a learned response would not be emitted even though there had been a large number of pairings between a stimulus and a response. Thus, in order to get a learned response, you need both habit strength and drive is symbolized capital E. This brings us to the next important component of Hull's theory, which is reaction potential. Reaction potential is symbolized SER and is equal to habit strength times drive. You can see that reaction potential would be 0 if either habit strength was 0 or drive was 0. Reaction potential is mainly the probability of getting a learned response to a given stimulus, and the major contributors to reaction potential, as we just noted, are habit strength and drive. But other factors also contribute to reaction potential. As we go through these other components of Hull's theory, it may be helpful to refer to the abbreviated diagram of Hull's theory, which has been furnished to you. One factor that influences reaction potential other than habit strength or drive is incentive motivation, which is symbolized capital K. K has to do with the desirability of the goal object. It is assumed that to a hungry animal, a larger pellet of food would mean more than a smaller one. So K is defined in terms of the weight or quantity of the incentive being used in a learning situation. The larger the incentive, the larger is the value of K. But K does not influence learning. It influences performance. According to Hull, by increasing K, you increase performance, but you not influence the learning process. This led to a very interesting prediction, which was subsequently confirmed, that animals learn as rapidly and as well for a small incentive as they do for a large incentive, but they perform differently for a large incentive than they do for a smaller one. Another component influencing habit strength is V, capital V, which is simply the intensity of the external stimulus. The greater the intensity of a stimulus, the greater the probability of a response to it. With these new factors, reaction potential is equal to habit strength times drive times stimulus intensity, or V, times incentive motivation, or SER equals SHR times D times K times V. There are also factors which operate against reaction potential, or against the probability of emitting a learned response. One factor that operates against reaction potential is called reactive inhibition and is symbolized I sub R. The concept of reactive inhibition is simply Hull's realization that performing any kind of response takes work, and work results in muscle fatigue, and muscle fatigue operates against the emission of a learned response. Conditioned inhibition, symbolized SIR, is a second factor that operates against reaction potential. Conditioned inhibition is the learned response of not responding. When an animal is fatigued, simply not responding is reinforcing. So there is the conditioned response of not responding that must be subtracted from reaction potential. Combined, IR and SIR are referred to as inhibitory potential and are symbolized SI with a dot over the I, R. Because these factors are operating against a response, they must be subtracted from reaction potential, and when they are, we have another new term. When the inhibitory potential is subtracted from the reaction potential, we have what Hull referred to as the effective reaction potential, which is symbolized SER with a bar over the E. Thus, we have a number of positive contributors to the emission of a learned response to a given stimulus, and we have some negative contributors, and the combination of the two will indicate the probability of a learned response being made. Hull also believed that there was another inhibitory effect that was not specifically related to anything, but it came and went in an unsystematic fashion. In other words, this was Hull's recognition of the fact that his theory was far from complete, and predictions from it could only be probabilistic. There were many things happening both inside and outside the organism which influenced whether or not a conditioned response would be made. So the figure that you arrive at when applying his theory is not entirely accurate. Rather, it provides a statistical estimate of whether or not a learned response will be made. This inhibitory influence that exists in different amounts from moment to moment is what Hull called the oscillation effect, which is symbolized SOR. This, too, is subtracted from the effective reaction potential, and when it is, we have the momentary effective reaction potential, which is symbolized SER with a bar and a dot over the E. The momentary effective reaction potential is the effective reaction potential, SER, with a bar over the E, minus the oscillation effect. If this momentary effective reaction potential exceeds some threshold value, a learned response will occur to the stimulus. The threshold value that must be exceeded by the momentary effective reaction potential is symbolized SLR. If the momentary effective reaction potential does not exceed that threshold value, a learned response will not be emitted. Therefore, it's possible that sometimes a learned response will be emitted, and at other times a learned response will not be emitted to the same stimulus. This is explained by the different values of SOR, or the oscillation effect. In the early stages of learning, when the value of the momentary effective reaction potential is close to the response threshold, sometimes the momentary reaction potential will fluctuate below the response threshold, and at other times it will fluctuate above, because sometimes the value of SOR is large and sometimes it is small. As the association between the S and the R becomes stronger, the chances of getting a learned response each time the stimulus is presented will go up. Since there is a larger value of the momentary effective reaction potential, and subtracting SOR from it will make less and less of a difference. 4 response variables, or dependent variables, were investigated by Hull. They were the probability of a learned response to a given stimulus, the amplitude of a response, the latency of a response, which is the time between when a stimulus is presented and when a response is made to it, and trials to extinction. These four things were used as indexes of learning. They were utilized by Hull to determine whether or not learning took place and to what extent it took place. Now let's go back over the components of the theory by looking at the diagram. You'll note that it's divided in terms of three major aspects of Hull's theory. First, there are the independent variables, and as you remember, these are the variables that are actually manipulated by the experimenter. The experimenter can arrange these variables any way he wants to. For example, he can determine how much work is involved in the experiment by varying how much effort is necessary to press a lever, or he can influence the amount of work necessary by tilting a maze up slightly so that it takes more work to traverse it. N is the number of reinforcements involved. T is the total drive, which to Hull is the hours of deprivation preceding the experiment. The experimenter can also determine the amount of reward being used, and he can also determine the stimulus intensity of the stimulus being used in the experiment. As we enter the box, we leave the observable world and we enter the world of intervening variables. Much has been said and written about intervening variables. Many have questioned their usefulness, and others glorify them as being essential for psychological theorizing. An important thing to notice is that they are tied down on both ends to observables. That is, they are linked to the independent variables on the one hand and to the dependent variables on the other. Intervening variables are convenient fictions made up by the researcher in order to explain the relationship between the input variables and the output variables. Most of these we've talked about already. Work, of course, is related to IR and SIR, and they combine to make I.R. Number of reinforced pairings is also related to the amount of effort, and therefore fatigue, but it is also related to SHR, which is habit strength. Total drive has to do with both drive stimuli and the drive state of the organism. Little w, or the amount of reward, defines incentive motivation, or K, and S has to do with the stimulus intensity, which is related to some internal events having to do with the central nervous system. These internal events that vary along with the magnitude of the external stimulus are symbolized V. Next, we have the positive contributors converging upon the reaction potential, and we have the negative contributors comprising the inhibitory potential. The positive and negative factors combine in a manner previously stated to become the effective reaction potential, which is symbolized SER with a bar over the E. From that is subtracted the oscillation effect, and when the oscillation effect is subtracted from the effective reaction potential, we have the momentary reaction potential, or SER with a bar and a dot over the E. Now we come back to SLR, which is the response threshold. This is the value that must be exceeded by the momentary reaction potential before a learned response can be emitted. When momentary effective reaction potential exceeds SLR, it can be translated into behavior in one of four ways. Response amplitude, symbolized capital A, response latency, symbolized STR, trials extinction, symbolized little n, or the probability of a response, symbolized little p. Usually, in an experiment, one of these response measures will be used as the dependent variable. Sometimes more than one will be used, but not very often. Note that the whole purpose of the intervening variables is to better understand the relationship between input variables and the output variables. Next, we'll leave the particular components of Hull's theory and turn once again to a few general features of his theory. Another important aspect of what he says concerning the learning process has to do with secondary reinforcement. When you take a neutral stimulus, that is, a stimulus that has no reinforcement value, and continuously pair it with primary reinforcement, that is, drive stimulus reduction, gradually the previously neutral stimulus will develop reinforcing properties of its own. For example, if you're using food as a reinforcer for a hungry animal, and each time the animal is presented with food there is a light present, that light will gradually develop reinforcing properties, and it can be used to condition another response. In other words, the light becomes a secondary reinforcer through its pairings with food. The concept of secondary reinforcement is vital in understanding what is probably the most complicated part of Hull's theory, which is the fractional antedating goal response, symbolized little r sub g. Imagine we have a T-maze and we're trying to get an animal to make a right-hand turn at the choice point. A T-maze is comprised of a start box, a long runway, and the T component. The place in the maze where it's possible to turn left or right is referred to as the choice point. Arbitrarily, we're choosing the right end of the T-maze as the correct response. Hull developed his notion of the fractional antedating goal response mainly in an attempt to answer what seems at first to be a very foolish question, and that is, even understanding everything we have said so far about Hull's theory, and noting that the animal will in fact learn to run this T-maze the way we want him to, why does he ever leave the start box? In other words, Hull thus far in our discussion has not been able to tell us why the animal ever leaves the start box in this kind of learning situation. So in order to answer that question, he created the idea of the fractional antedating goal response. The explanation runs something like this. In the early stages of learning, the animal finally makes it to the goal box and is rewarded with food. Food, of course, is a primary reinforcer. We learn that stimuli that are paired with primary reinforcers come to have reinforcing properties of their own. So the stimuli in the goal box that were experienced just prior to food should become secondary reinforcers, and let's say they do. Now we have two kinds of reward operating in the learning situation. Primary reward, which is the food, and secondary reward, which are all the stimuli that have been paired with food. Now the animal no longer needs to make it all the way to the goal box to be rewarded. He just needs to encounter a secondary reward, which he will do before he actually reaches the food. Now the stimuli paired with secondary reinforcers also take on reinforcing properties, and gradually this process works back all the way to the start box. Thus, when the animal leaves the start box, some responses he makes will be rewarded with secondary rewards, and others will not be. The responses that bring him into contact with secondary reward most rapidly are learned, and soon he is taking the most direct route through the maze to the goal box. But this is only part of the story. Each time a secondary reward is encountered, it elicits a conditioned response. This is due to classical conditioning. According to the principles of classical conditioning, when a neutral stimulus is paired with reward, it will eventually develop the ability of eliciting the same kind of response as the reward does. In this case, food is the reward, and the neutral stimuli were all the stimuli along the route to the food. Food causes the animal to do such things as salivate and chew, so eventually the stimuli along the path to the goal box should do the same thing. In other words, after considerable training, when the animal encounters a secondary reward, it will cause him to salivate and make minute chewing movements, and these are called fractional antedating goal responses, or little r sub g's. A fractional antedating goal response is nothing more than a conditioned response given to a previously neutral stimulus. The r sub g is a response, and like any response, it produces stimulation. The stimulus that an r sub g causes is symbolized s sub g. R sub g and s sub g are inseparable. That is, whenever an r sub g occurs, an s sub g must occur. The situation we have so far is this. The animal leaves the start box and experiences a secondary reinforcer which elicits a fractional antedating goal response, which in turn elicits an s sub g. The important thing about the s sub g is that it has overt responses conditioned to it. So when an r sub g occurs, it produces an s sub g, which in turn triggers the next response through the maze. Eventually, only those responses that bring the animal into contact with reward, both primary and secondary, will survive, and we say the animal has learned the maze. This whole process is referred to as chaining, and it can be seen that chain behavior is governed both by external stimulation, secondary rewards, and internal stimulation, the little s sub g's caused by the r sub g's. So the answer to the question, why does the animal leave the start box, is that doing so brings him directly into contact with secondary reward, which rewards the response of leaving the start box. But not only does the secondary reward leaving the start box, it triggers an R sub G, which produces an S sub G, which triggers the next overt response through the maze, and on it goes all the way to the goal box. Because any number of overt responses can be elicited by any of the little S sub G's, there are many alternate routes to the goal box, but the route that is most likely is the shortest one because it brings the animal into proximity of the rewarding stimuli most rapidly. The most direct route through the maze, whether a T-maze or a more complicated maze, is the most rewarding one, but it's not the only one, and that leads to the last major component of Hull's theory that we are going to talk about. This last concept is related to the fact that there are many ways to traverse a maze. The shortest one is the one that is preferred, but if that is blocked, the animal will go to the next shortest one, and if that's blocked, he'll go to the next, and so forth. Hull called this the habit-family hierarchy. The habit-family hierarchy simply refers to the fact that in any learning situation, any number of responses are possible. The one that is most likely is the one that has been reinforced the most, or the one that brings about reinforcement most rapidly. If that particular way is blocked, the animal will prefer the next shortest, or the response that has been reinforced the second highest number of times, either one. If that one is blocked, he'll go to the third, and if that is blocked, the fourth, and so forth. Thus, after learning, there is a family of habits arranged in preferential order. And with that, we will end our discussion of Clarke Hull's theory of learning.